Okay, so just as a reminder, we are zooming in and in towards the airplane, right? So in the beginning, we use the vortices to explain the wake of the airplane. And as we are zooming into the airplane and looking at the effect of both the trailing vortices and the bound vortices, we can now use the lifting line theory to guide our aerodynamic analysis and design of airplanes and look at how different designs of the planform is going to affect the performance, the aerodynamic performance of airplanes. So this week we are going to be looking at the effect of taper, sweep, and twist, and also the effect of dihedral and multiple wings. And by the end of the week, we are now also getting to more theoretical aspect of why there is lifting line theory, right? Why is the flow around the airplane dominated by these vortices? And this theoretical analysis is going to allow us to zoom further into the airfoil and look into the bound vortex through the wing, not just as a single vortex, but as a collection of vortices that explains the flow around these airfoils. Okay, so this is the agenda for this week. And again, like the quiz that is going to cover all this lifting line theory and airfoil theory is going to be happening October 16th. Okay, so first of all, we are going to discuss the flow near a tapered wing airplane. And let's start by looking at a recording of something that happened, I think, 2021. And let's just see what's going on. So we should see an airplane flying towards the left. It's a big transport airplane. Can somebody describe what you see happened? Let's look again from here. Okay, the airplane is turning towards us. Actually a little bit similar to what we saw previously, right? When the airplane is flying just into the wake of another airplane. But in this case, there is no other airplanes around. So what happened is, as the airplane was turning towards us, one of the wingtips stalled. And a stall of one of the wingtips results in a massive loss of lift on just that wingtip. And as a result, the airplane flips over and crashed. So this accident involves the C-130 transport airplane. And one of the features of this airplane is the taper on the wing. And of course, in this incident, the pilot and his crew made a lot of errors, and which compound with the loss of one of the engines led to this crash. But this is actually an opportunity for us to look into actually why a tapered wing airplane is more likely to stall on one of the tips. Right. In this case, the airplane is turning towards the left, which means the left wingtip is seeing less airspeed, right, than the right wingtip. Of course, that's part of the reasons why it stalled. But like, we're actually going to look into using lifting line theory to look at the induced flow, not around the airplane, but actually exactly on the wing themselves, and look at how can the induced flow explain why the outer board portion of the wing actually may stall first. All right. So in this case, let's actually take the airplane and work it out, like in the blackboard. So one of the effect of a tapered wing, just like what you are doing in the homework, right? It has a smaller chord towards the wingtip and the bigger chord near the wing root. As a result of that, just like in our previous example where we have flaps, right? We have more lift in the inboard portion of the wing and less lift on the outboard portion of the wing. Okay, so in a quantitative calculation, we are going to approximate the lift distribution as many small segments, right? And like in between every two segments where the lift changes, we have a trailing vortex coming out. But for this qualitative calculation, let's just use the crudest approximation for the lift distribution. So let's just imagine we split the wing into 4 equal portions. And we are going to approximate the inboard half of the wing to have twice as much lift per span as the outboard portion of the wing. Okay, which means if the circulation of the bound vortex in the outboard portion is gamma, then in the inboard portion, the circulation is going to be 2 gamma, right? Okay, so what does that mean for the strength of circulation of the trailing vortices? Can somebody tell me, like, how do you calculate the circulation of the trailing vortices? They are also gamma, right? So the reason is that, as we said, a vortex has no ends. So whenever you have multiple vortex coming into junction, so for example, we have a vortex going into, let me see, the direction is right, this direction, this direction, this direction here. Okay, whenever you have a junction like this, think of it as you have current, right? You have a current of gamma going this way, and you have a current of 2 gamma that way. That means there has to be a current of gamma going into that junction, right? Because otherwise, over here, you have a problem of not having continuous vorticity. So that means on the trailing vortices, we have to have gamma here, we have to have gamma here because this goes out, right? And here we have to have gamma going that way and gamma going that way, right? Okay, and actually over Friday, we are actually going to explain why this is true, right? Why do we have to have almost like a conservation of vorticity? That means if I have a gamma coming in, I have to have 2 gamma coming out. Why that is the case? And it turns out we can actually derive this not even using any Newton's law. It's just a mathematical fact directly coming from vector calculus. Okay, right. But in this case, we are going to look at the induced flow of this collection of vortices on the following points. We are going to look at this point on the center of the outboard part of the wing, on the center of, basically at the center of every quarter of the wing, we are going to look at what is the induced flow. All right. And we have to pay special attention to the sign of the induced flow. Does it go upward or downward? Right. Just to make it clear in the very beginning, all these vortices are on the same plane. They are actually on the xy plane, right? So if you choose this as the origin, okay, it's the center of the bound vortex as the origin, z points upward, then all of these vertices have 0 z, right? Okay, so they are all in the xy plane. And the points we are also looking at are also on an xy plane. So that means 2 things. I mean, if you look at Piazza, I actually answered one of these questions by saying that if all the vortices, they are pointing in directions in the xy plane, and also r, right, in the Biot-Savart law, which means r represents the vector that points from some segment of the vortex to the observation point. That vector is also in the xy plane. If 2 vectors are in xy plane, right, dl and r, then dl cross r, well, it's not in the xy plane because cross product actually takes it out of the xy plane. The cross product will only have a z component. right? That's if you think about what the cross product does, and they use your right hand rule. If I have two vectors in the same plane, then the cross product has to come like orthogonal to that plane. Right. You can also figure out algebraically, just look up for the what cross product does for a three-dimensional vector. You can also figure that out. If two vectors have zero z component, then the resulting cross product is going to have zero x and y components. Okay. All right. So in this case, we only need to figure out the z component of the four induced velocities, but you have to be careful with the sign. All right. So so let's figure out the first question. What is the induced flow at the center of each of the four sections of the wing, right? So basically these 4 points. And we are also have to answer how much does the induced flow change the local angle of attack? So what does that mean? That means the airplane flies right forward. If you take the frame of reference of the airplane, then the airplane doesn't move. The air, the free stream, comes towards the tail of the airplane, right, in the x direction. Okay, and there is induced flow over here. So if the induced flow goes downward, that means the compound velocity of the free stream and the induced flow goes slightly downward, right? Okay, so it mostly goes towards the tail, but now slightly downward. Does a downward flow increase or decrease the angle of attack of that cross section? Decrease. If my angle of attack originally is 0, now the airfoil sees a downward flow. So let me just draw it over here. Right, let's say this is a cross section of the wing. Okay. And if I have a velocity that's going downward, right, the angle of attack is going to be decreased, right? This airfoil now sees a negative angle of attack. On the other hand, if the induced flow is positive, which means the induced flow is in the positive z direction, the compound velocity is going to go slightly upward, and that increases the angle of attack, right? So here, the second question is, okay, how much does the induced flow change the local angle of attack? And this question is relative. Okay, this is relative means is the angle of attack changed more here compared to here? Okay, so that's the question. And the third question is which part of the wing stalls first, assuming the stall angle of attack depends only on the local angle of attack of that cross section. All right, and then the last two question is how much does the induced flow tilt the local vector backwards? Again, like the how much depends on, the question is like relative. Does it tilt more here or here, right? And the final question is, well, you don't have to calculate the induced drag, but like how can you use the tilt angle? Like what would be the procedure? If you can calculate the tilt angle quantitatively, how would you use it to estimate the induced drag? Okay, before I have you form teams to come up, is there any clarifying questions I can answer? No? Okay, so let's get started. And as you can see, this is a really kind of a simplified version of what you have to do in the homework, right? So if you can figure this out, I think you can pretty much figure most of the homework out. All right, please.
Which is the speed limit. like we're taking our reference point here, and then basically like this angle would be 0 and this would be negative 90. Like, is that what we're looking at?
Uh,
Like you're going all the way out to like infinity.
yeah,
Is that like should we take it out to infinity? Is that the right way to do it?
that's right.
Okay.
Yeah.
Cool. Thank
And
you.
by the way, I think we're looking at these 2 points and these 2 points. So we're dividing the wing into 4 parts,
Oh, I
right?
see
And
what you're saying.
looking at the center of each of the 4 parts.
It's like b over 4 and 3b over 4?
Yes.
Okay, cool. Thank you.
That's right.
So like here, right? From this. Oh, I always do that. Oh, yes. Then Ray was like,
4 pi times the orthogonal distance.
oh yes, right. So or that it's the point on this and that. So when it's in the middle,
Exactly.
like there isn't any contribution from like the boundary.
So that's the part that's easier than the whole point, right? Yeah, there's nothing from all the one vortices.
I feel like these two elements are that and is like it's just like circle like this guy is pointing down the center. Wait, where's your like point?
Oh, but that was off the back. So we can assign stuff.
Okay, so we have is it this cross this or is this cross right, if you use the right sorry, R. I don't know, R be like this. I feel like R, when they're in the same plane, don't necessarily. Oh yeah, it's going on.
Oh, I agree.
Like, isn't it like the perpendicular? It's like straight. Wait, then what it says that with all of this? That's like here.
No, I think
Maybe.
actually no. Wait, no, this one.
Yeah.
From the
Sure. So B over A or B over A. Right. I thought you would just kind of R B over maybe it's A over A.
Oh, we go from this one is good. We always go downwards. That's why. Yeah. The shortest distance to the
Like 90 minus 0 and infinity. So all the angles are right. The point from so when it's all the way out 0. Wait, no, when it's all the way out, we want this to be 1. Oh, B. Yeah, right. Oh, yeah. We also have this one too.
I think it's the algorithm. Well, I guess it doesn't really matter because we just conceptualize it afterwards. We just want it to be one.
Oh, but this time.
It's one when it's all the way over here. Or it's either 0, 1 when it's all the way over here, it's either 0, 1 when it's all the way over there. So we just know that it's one. And then the sign would be down, so it's minus 1. So I guess this is what.
I think this is supposed to be this positive minus negative. I think it's supposed to be like the magnitude of the positive. But anyways, just pick up. And then this one is also, I think, you're right that it should be. I think okay, number 7. There's a different direction. Why did you get that?
So this one you have to control.
It's like these are in the same direction, but like sideways point.
Oh, this is the first one. Yeah.
Oh my gosh. So much fun. But now we're swapping the side.
Wait, which one are we doing?
You want to do this?
One of them
Wait, from this?
Oh, it's okay, yeah, just I did like
They're both away. Yeah. So they this one is 6 over down. Yeah, this one there. So yeah, this should be also. Oh wait, also it's going to be going down. Oh, right. 5. This distance is 7.
Okay, yeah, that is so much faster. Okay. Exactly the same.
This one is.
Yeah. Is it same direction? Yeah, down. Okay, I'm just gonna add like a sure.
I'm trying to figure out what the sign is. So like.
It's
going out. You said out of the this one? Say this one. This is going into the board. So what is that positive? Is this positive? And then
so the vector for arrow the movement would be like plus
then this one's out of the board.
oh yeah.
And that one's also
yeah, if y is right.
or is it no, it's into the board. Curls around into the board. So that one's
You have air will have
oh,
component.
is that what it is?
Ah, okay. So then it's just straight. Yeah. So like for
I can. Yeah. So it's c over x, like this over b is tan theta. It's like r. Yeah. Arctan theta. Oh, yeah.
It'd be great if we can actually calculate the value, at least to know which one is bigger.
Okay.
I mean, it doesn't have to be very precise, right? But like roughly, I mean, even if you have a single digit.
Yes. Yeah. No, the
It's
fractions
useful.
are not.
Yeah. That will help you figure out which one is bigger.
Simplify the 4.
Don't really have to simplify. Just if you have a sense of which one is bigger, then it's enough. Which one you're trying to work out?
We tried to do these two as it got them canceling each other.
Exactly. Yeah.
Okay, and then we're trying to do this.
Yeah. Okay.
I think we're a bit confused with the angle, like when it's negative, when it's not negative. So we're trying to think like.
Yeah, so I usually figure out the magnitude using equations and figure out the direction using the
Okay, so you can kind of ignore the.
Yeah, so if you just want the magnitude, always take the big angle minus sine of the big angle minus sine of the small
So
angle.
it's going out. If it's like here, and then here, it goes out. Yeah. But if it's also minus here. That makes sense. Okay. And then yeah. Okay, and then that one might be. Then how is that different than multiple 90 and 0 the same age as last age as well? Well, no, this one is here because it's the same thing like that. But this one definitely in order to get this from this one, you have to just out. Oh, so just the point is out. This one, to get to the point, you have to go all the way around. So it was 3 times plus 1 8 all the way around. It doesn't go all the way around. It just goes, which is still easy. This one would be, this one would be all the way around, out of the board. Yeah. Goes first. So that one.
Whichever one has the. Wait, no. We'll just say whichever one's bigger.
Oh, I went all the way from here.
Wait.
My bad.
Like, this is going to be bigger.
No, I also did this.
No. I'm saying the downward velocity here. Like, I was
adding this part.
So it's going to make it steeper.
Hang on. That's what I think.
So it's like, oh, sorry. I think it's 3 inches. Wait, that's
No, but it's asking which part of it stalls first. It should be one.
So then this point would be 1, 2, and then this point would be the same as this point. You mean opposite?
Wait.
I guess so. Opposite. I should stick with saying this is 1 So
Did we though? Did you do arc2?
the same variations of like 90 degrees to 0.
Essentially, but also like, I don't think it's not because like if these things cancel, then it makes sense that this velocity would be less than
Okay, so like this one gets like lowered by more.
Yeah.
So that means like this one has a higher angle to
Oh, so it's gonna stall.
Yeah.
Oh, okay, I forgot what stall meant. I'm just gonna say like
Okay. It was 1/2. So just by alpha. How much did you already did that right?
I mean it tilts it a negative amount backwards, so I mean
How did you not have 1/8?
Still like the X component of it.
Oh, these two, they're both.
okay, so I guess it's still moving.
That's all right. How like this.
That's 3/8.
How does that? How do you see that in the?
I guess this will probably give us like this plus and minus off, but otherwise,
Yeah.
but like, it's still moving this way. So would the drag still be in this direction? No idea.
It's whatever the opposite of the X component is.
This distance, same as that.
Well, I guess that's not much. It's not, yeah, it's not gonna be meters per second.
Can you?
All negative.
Oh, yeah. Good work, good work. Oh, do we agree with that? No. Precisely. Why do we agree with that?
Or the.
Actually, maybe not. Maybe we do agree with that. Because 96 divided by 4 is 20. Okay, so
We're about to agree with that.
Yeah.
This one's pointing down, we're gonna agree with it, this is down. Just think of a spiral.
Is that always extreme?
Yeah, so if you or if you use the old weight, which is the old weight, if they
How does make this going down? These two are going down. Then I think this is 1 and 4.
Does it depend on this math? Depends on overall circulation, because I'm cutting out.
yeah, exactly. It's opposite to the direction.
Like we have.
It seems like a bad thing. It's probably easier to now for
Doing these flow change the angle of the task.
You have
Overall down. No, this is mentioned on this is weird. That's bigger. He said, well, just like in here.
This is changing something further down.
Yeah.
That's it.
Yeah, that's good. So the tip stalls first, right?
How do you get to like the velocity of the
That's I.
So the
Okay, so basically know that the free stream is going in this direction, but they choose the flow goes in that direction. So the airfoil cross section basically sees the that and goes slightly downward.
which means the lift is always orthogonal to the free stream seen by the airfoil cross section.
Yeah,
I think make more sense.
So
that means the drag is not of the same strength.
so no, sorry, which direction is the free stream?
Greater change.
So this is the free stream of the airplane. Okay. And the free stream seen by the cross section is what? So this is free stream, induce the flow is down, right?
Yeah, yeah.
So
So
at the
like
top.
it would be like this.
Exactly, yes.
So yeah, this arrow is like that.
Lift is in what direction? Exactly. Yes. That would be the yeah. But like right now, we're not considering the drag of the airfoil yet.
Okay.
We're just saying if the lift vector is tilting backwards, the backward component of the lift is actually induced drag.
Okay, yeah, that's like
Yeah, so there is a slight discrepancy between the free stream of the airplane and the free stream of the cross section. Right. That means there is a component of the lift of the section that is actually drag of the airplane. That's induced drag.
Should we be calculating that for question 2? Or is
Yeah,
it like
for question 2, you just need the relative magnitude of this. It's
Okay.
because which one is larger. You don't have to be very precise in the calculation.
is it, are we correct in really that 1 and 4 have the same?
Exactly.
Okay.
Yes.
Wait, the area of like where the angle of attack is. Like right now, we're doing like this, like, oh my god. Which part of the wing stalls first?
assuming the stool angle depends on the
Local angle of attack.
said I'm like
Number 4, almost.
I thought like the wing's angle of attack was like that, but it's not updated. Like it's only on that.
So basically, it's gonna be the same angle as how much the
This is down.
yeah, just row.
so the lift by definition is
Like I was
so the lift of
I just don't want to
Then if it has a greater yeah, doesn't that mean it has more lift?
so if the frequency by the cross section
Yeah, right? So this has less lift than this does. Here. The least amount of lift.
I guess you want to study the volume. I think you want like the multiply area or something. You know, like pi b over 2 squared or something.
Parts of the left.
Or area of the wing.
as the air is like
I think.
It's like
Like, that's how we're in a real plane. It's like my, I think it was, yeah. So I was trying to make it at an angle, but I can't draw it at an angle. Here. And it's drawing down. Then maybe we're adding.
But isn't it like the
Point of view of the body.
yeah, we could like do pi b over 2 squared. There's like b times the velocity.
It's also not like what we're calculating.
Oh, I guess we want to find the full volume, not just the area. Like momentum.
It's like flow.
How much is
Easy to think, just
So remember we like found the volume of the cylinder, we multiplied it by rho, and then we multiplied it by the air.
I thought that the length of the cylinder was way
it's like this, like this? It said, oh, she's a bad.
Yeah, v of the like.
We never needed the
Like v. Or the fourth. We never needed that. Oh yeah.
I think it's just like you put something.
But your place well.
So instead of using the area, just use it.
Yeah, okay, so I guess this is just.
Okay, so let's actually go back and I think all of you got the first question, right? And for the second question and onward, let me explain quickly. And if you have questions, let's ask after I explain it. So first of all, what is the induced flow at the center of each of these section of the wing? So here, I think I saw all of your calculations, but it is pretty clear that the induced flow here and here are both downwards, right? And the induced flow downwards here is small, and the induced flow here is large, right? And actually, it's more than twice as large as the outboard section, right? I think all of you got, maybe not all of you got the quantitatively the answer, but I think all of you get the downward flow in the inboard section being more than twice as large. All right? All right, okay. So now the second question is, how much does the induced flow change the local angle of attack? So this question is requires imagination in the third dimension. So here I have a cross section, and if the V infinity of the free stream goes exactly horizontal, then the downward induced velocity actually makes the total velocity seen by this airfoil cross section to be downward, and that decreases angle of attack, right? So that airfoil section is actually seeing a smaller angle of attack if there is a larger downward velocity, which means if I have a large downward induced velocity, I have a smaller angle of attack. And here on the outboard section, I have a larger angle of attack. Right? Of course, that means the outboard portion of the wing is going to stall first if I pitch the whole airplane up, right? And that combined with the turn we were seeing in the accident, right? So during the turn, the left wingtip also sees a smaller aerodynamic pressure. So for the airplane to maintain balance, the left wingtip has to have its aileron also pitched up, right? So basically overall, the left wingtip is much more likely to stall than either the right wingtip or the inner portion of the wing. Okay, so that led to the accident. Okay, and the final two questions is how much does induced flow tilt the local vector of lift? Now the vector of lift, so there is a discrepancy between the definition of lift for the whole airplane and the definition of the lift for the airfoil cross-section. The definition of lift for the whole airplane is orthogonal to the free stream seen by the airplane, right? So the lift of airplane is always going upward if the airplane is at level flight. However, the lift defined on that cross-section is orthogonal to the tilted free stream seen by that cross-section. So that is the lift of the airfoil cross-section, right? Okay, so both are orthogonal, but orthogonal to different vectors. So if I have a larger induced flow downward, it tilts the cross-sectional free stream downward more, thereby tilting the lift of that airfoil backward more. So it is the horizontal component of that tilted lift vector that actually contributes to the induced drag. So the induced drag is basically, let me just call it DI. That's so if you basically estimate for every cross section how much does the lift vector tilt backwards, and for that cross section calculate the lift and calculate the angle, multiply the lift by the sine of the angle, right? And sum it up, it'll be the total induced drag of the airplane. Actually, this is the induced drag reported by AVL when we look at it the Friday a week ago. Okay, and it reports two induced drags. One induced drag done by this calculation, by like how much the lift vector is tilted backwards, and another induced drag is by looking at the far wake, looking at all the vortices coming out and integrating the kinetic energy in the wake. Okay, so these two induced drags should be exactly equal if the calculation is precise, in the sense that if I discretize the airplane into infinitely many segments and the integration is exact. But of course, we always use finite number of vortices in our calculation, and I think last of the Friday a week ago, you see there is something like 1% difference, right, between the two induced drags, and that kind of gives you also an indication of how much error okay, so that error is due to the discrete nature of the lifting line theory. It is not an error of the drag itself, because the drag itself also has error of the lifting line theory itself, right? The lifting line theory assumes a bunch of things, which we're going to explain this Friday, right? Which part of the lifting line theory is correct, which part of the lifting line theory is an approximation. Okay, all right. So that's it for now, and I'm just going to go over a little bit on like the kind of numerical calculation that was done. So this is what you see as a lift distribution of the different tapered wings. So as you can see, for example, when lambda equal to 0.2, which means the tip has only 20% of the chord length as the root, you can see that the lift, the downward, the induced flow is much less right near the tip region compared to the center region. That's consistent to the calculation you've done. On the other hand, if the taper ratio is greater than 1, which you never see in an actual airplane, you have more downward flow, you have more induced flow at the tip. And as a result of that, if you have a increasing taper, you have a the CL of that, the lift coefficient of the different cross sections is going to be distributed in a more and more unbalanced way with higher lift coefficient near the tip, which means it'll stall first, right? Okay, so that's any questions on what we are showing over here? This is induced flow, how it looks like, and this is a calculation of how this coefficient is distributed. Right, for a rectangular wind, because of the strong vortex over here, we have actually a lot of downward induced flow near the tip, right? That reduces the angle of attack and reduces the CL. While for a strong taper, it's the other way. As in your calculation, because of the vortex, because there is a lot of vortex not on the wingtip, right? This vortex is not on the wing in the inward portion of the planform. Actually induces upward velocity. They counteract with the effect of the tip vortex, which is weaker also in this case. And that's the reason why the induced flow is less over here, which means the angle of attack and lift coefficient is higher over here. Okay, any questions? All right, and in your homework, you are also going to see not only the effect of the taper, but also effect of a sweep. And you're going to see that this effect we are seeing is going to be amplified actually in the case of sweep. And in your homework, you should actually get not only not just a smaller downward velocity here, but actually upward velocity at the outward portion. And if when you're doing the homework, you can think a little bit like why that is the case, like why a strong backward sweep is going to amplify this effect, making actually, if you unless you twist the wing, you're going to make tip stall even more likely if you have a backward sweep. Okay, so I'm going to have office